Hello, I am audible.
Yes, sir, audible.
Hello, I am audible. Or Ratnasri, I am audible or not?
Yes, sir,
Please
audible.
just confirm. Then I will start the session.
Audible, sir.
Okay, I am audible.
Yes, sir, audible,
Okay,
sir.
okay. Your voice was not coming previously. Okay, now you are also audible. Okay, now I will start the session. So the slide is visible very well,
Yes,
and
sir, visible,
slide is
sir.
also moving.
Yes, sir,
Yeah,
moving, sir.
okay, fine. So, welcome in hydraulic engineering, uh, week 6 PMRF live TA session. So, I'm Om Prakash Maurya. So, today topic is about the introduction to open channel flow and uniform flow. So, basically, from the very basic, you all know the open channel flow is nothing but the free surface flow actually. Free surface flow. And free surface flow have the lots of characteristics. One of the major characteristics it is flow due under the gravity. That is the slope. The pipe flow, pressurized flow, it may chance to flow from this direction to this direction because due to the pressure. But in the open channel flow, generally always flow in the downward direction if slope like that. And the free surface will be there on the. And velocity distribution you all know in case of pipe flow. Anybody join? I think someone joined. Okay. Okay. So this is all about. Okay. I was talking about the velocity diagram. So in pipe flow, generally velocity diagram we have seen already in the previous classes. Let's suppose this is a pipe. Why we are focusing in the velocity? The reason behind it because all the characteristics of the fluid we can calculate if we know the velocity and all, velocity and some geometric parameters and all, but velocity is the major thing. So every time in case of the fluid mechanics we discuss about the velocity. So that's it about velocity. So velocity diagram in case of the pipe flow, if this is a wall, if this is a pipe wall both sides, then here at the wall your velocity is 0 and at the mid your velocity is very high. But in open channel flow case is very different comparatively. So what here, open channel flow might be possible in the pipe, but if we look the cross section point of view, but pipe should not be filled completely. So this is also open channel flow. But here I am talking about the water is full with the completely full in the pipe. Okay, in case of open channel flow, so your velocity if water is flowing like that in this direction, your velocity diagram like that. Here due to the dip phenomena, your velocity will be less little bit from this location. Dip phenomena is due to the air and the secondary circulation. So that's all about the velocity diagram. Okay. For simplicity, generally in case of the open channel flow, we always try to consider at undergraduate level your rectangular type of channel. So we always consider these things. That is a rectangular channel. Sometimes we also prefer parabolic, sometimes circular also, sometimes V type also. Okay, this is that. So now I want to talk about the rectangular channel. So this is width of the channel and this is the depth of the channel. This is the Y. So here area is what? Area is B into Y, and perimeter is what? Perimeter is basically these all things. So in open channel, we always consider the weighted area. So weighted area is B into Y and weighted perimeter PW. Sometimes we represent by P only, here only A. So what is weighted perimeter is nothing but the addition of these all things, these all sides. So B plus Y, one time Y, and here one time Y, that is 2Y. So B plus 2Y. But sometimes if channel is very wide, if like that, if channel is like that, this is Y and this is B. So here B is very much compared to Y. So what we did, when we calculate these things, your hydraulic radius is nothing but the ratio of these two things, area by perimeter, that is weighted area by weighted perimeter. So here we will put the B into Y plus B plus 2Y. So if the weighted B is very much than Y, then what we did, we have neglected Y from the bottom, that is from denominator, because of the simplicity in the calculation. When we do the calculation things, then you will understand easily why we are eliminating. So only B is remaining here because this is very less comparatively this, so there is no harm to neglect. So it will be removed, only Y will be remained. So for wide channel, your hydraulic mean radius is Y. So this is very basic fundamental things about the open channel flow. So here I have some questions. For question 1 is nothing but calculate the weighted perimeter for a rectangular channel having top width 4.5 meter and depth is 3 meter. Yes, please try to solve this question and give the answer. Then using the first question, we will solve the more geometrical parameters. Okay, please, Ratna, you just try to solve the question. Well, let me share in different way so I can see the. Okay, now I can see. Question is visible?
Yes, sir. Visible, sir.
Yes, please try to solve the question number 1. Calculate the weighted perimeter for a rectangular channel having the top width is 4.5 meter and depth is 3 meter. Okay, you are telling the option D is correct for that. Okay, let me check. So here the channel is rectangular and width is given 4.5 meter and depth is given 3 meter. So your perimeter is nothing but addition of these two things. So 4.5 plus 2 into 3. So it will come 6, that is 10.5 meter. So 10.5 meter is the correct answer. Now I am requesting just please try to solve the R value, hydraulic radius. What is the value of R for this question? Hydraulic mean depth. I will give you some.
Sir, R equal to 1.28, sir.
R is equal to 1 point.
28.
Okay, 4.5 into 3. If you will calculate how much you will get.
13.5, sir.
Okay, okay. 13.5, that is the area of weighted area AW, and R your will be 13.5 divided by 10.5, and this is come out how much?
1.8.
1.8. Okay, okay, fine. 1.8. This is about the hydraulic. If I see this is the hydraulic radius. Now I want to know from your side what is the value of hydraulic diameter. This is the hydraulic diameter. This was the hydraulic radius. Okay, please try to solve this hydraulic diameter.
Sir, hydraulic mean radius are equal to 1.28, sir.
Okay, you
1
are
point.
telling the 1.28. How you will calculate these things? What is the formula for this? Can you please tell me? No, no. What was your hydraulic radius? Hydraulic mean radius or hydraulic radius? How much? 1.28. Right.
Yes,
Okay.
sir,
Okay.
1.28, sir.
Okay. Yeah, okay. Okay. 1.28. That's fine. Well, just I have calculated 1.28. It is coming. Okay. No issue. But you try to. Are you calculating the hydraulic diameter?
No, sir.
Okay. Let me tell the formula and all. Okay. This is a very, very unique concept. 28 meter. So this is that. Now I want to go on the next slide. A new slide. Okay. One blank slide is here. So what is actually hydraulic diameter is nothing but, let me go with from the very basic. In case of open pipe flow, we have studies about the already Reynolds number. If it is diameter is D, so what is the Reynolds number? Rho V D by mu. This is that.
OBD by mu, sir.
Yes, if it is a rectangular type channel, rectangular type your duct, this is the circular, but this is a rectangular type. And how you will calculate these things? For calculating these things, we have one formula. What is 4 area of cross section divided by perimeter? Let me check here. If DH, using this formula, if DH will come out equal to D, then it will be good. Then it will be a right formula. Let me check. So 4 AC means what? Pi by 4 D square, right? And here is perimeter is how much? Pi D. So pi pi cancel, 4 4 cancel, and D cancel. So DH is equal to D. So this formula, that is 4 AC by P, is giving what? In case of pipe flow, it is giving D. So at that place we can replace your RE is nothing but rho V DH divided by mu. So it is applicable for all cross section. For all cross section. On what is DH? DH is nothing but 4 AC divided by. Are you able to understand what I am telling?
Ah, yes.
Okay, 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 fine. So now for can you please calculate for if it is like that, rectangular duct, your B is there and Y is there. So what is DH? So area of cross section is what? B into Y, and your perimeter is what? Your perimeter is, here water is full, not the open channel. This is not the case of open channel flow. I am talking about the rectangular duct. So 2B, that is this B and this B, and plus 2Y, to 2B plus Y. So DH is how much? DH is 4B into Y divided by 2B plus Y. So here cancelled, 2by divided by b plus y. So this is a DH. So this is the DH in this case. Okay. The previous question was about what? Your channel. This time your channel is like that. Water is flowing, open channel flow. And your width was how much? The 4.5 meter, I think. And your depth was 3 meter. So now here hydraulic diameter is what? Hydraulic diameter is, now you will calculate, please try to calculate these things. Okay, are you able to calculate, or let me? Ratnasri, are you calculating, or I discuss? I begin the discussion.
I got the answer 5.14, sir.
Okay, okay, that's fine. Okay, let me discuss just. Okay, so here area is your 4. That is the formula. First of all, 4 into area of cross section. How much? 4.5 into 3 divided by your weighted perimeter. Weighted perimeter how much? 4.5 plus 2 times 3. Here here it not we consider the 2 times b because of because of the open at the top, because there is no wall at the top, so only these things. Now let me calculate. 4 into 4.5 into 3 divided by 4.5 plus 2 into 3. Okay, how much you get?
5.14,
Yeah,
sir.
it's fine. Okay, 5.4. So this is that. Now one relation between the hydraulic diameter and hydraulic radius. Generally, we know the radius and diameter relationship. Diameter is equal to 2 times radius. Generally in the geometric things, but here we are talking about the hydraulic radius and hydraulic diameter. Okay, now let me discuss on the new slide. What is the relation? Okay, so basically your hydraulic radius is equal to weighted area by, or let's suppose only A by perimeter, and here your DH is equal to 4A by P. So you can replace A by P with RH. So 4 times. Here your diameter, that is the hydraulic diameter, is 4 times of the radius, that is hydraulic radius. So always remember. Now let me calculate from the your RH was 1.28. So how much coming? 4 into 1.28. So this is coming on the 1.2, 5.12. So this is almost 5.14, the 4.5. So maybe we have calculated RH like that. How much RH? 13.5 divided by 10.5. So if we consider 1.28 little bit higher after decimal, 57, so it will become like that, no issue. 1.52857, so it might be chance it will become almost 1.54, closer to 1.54. 1.2857. Yes, it is almost 5.14 something something. So that this is the difference. Hope I think you understand what I was telling.
Yes, sir. Understands.
Okay, now coming on the next before. Okay, so second question is the Froude's number for a flow in a channel cross section is 1. What type of flow is it? Whether laminar flow, turbulent flow, supercritical flow, or critical flow. The Fr is equal to 1. That is your Froude number. I will discuss a little bit more about the Froude number. So please just give the answer, then I will discuss.
Critical, sir. Critical flow.
Yeah, it is very, very common thing. If anyone have done previously the open channel flow, then it is very easy to tell the. Okay, now I want to discuss a little bit more. Okay, Fr is nothing but it is the ratio of your inertial actually square. Fr square is equal to inertial force divided by gravity force. So inertial force, what is inertial force? In the previous class I have discussed, this force is due to the flow rate of mass flow rate, due to the mass flow or how much the mass flowing in the channel. So inertial flow depend on that. And the gravity flow is gravity forces depend on your weight of the body, weight of the fluid or not. Okay, so how it will come around your if you will calculate your rho v square by a, this is the inertia force, and gravity force will come like that, mg or rho g, that is basically weight, nothing but if you will calculate the weight on weight is equal to what, mass into these things. Or in another way we can also calculate if we talk about the unit weight. So this is what, weight divided by volume. So weight is equal to what, unit weight, that is your gamma if we denote by gamma, and this is also equal to rho z or gamma, and your volume that is the rho z, and volume is area into length. So this is that. If we put here the rho z, area into length, so this cancel and rho cancel, only remaining what, v square divided by gl, or we can say this is the y, because this is the length parameter, here the length parameter, so we can tell that this is the y. So fr is square is equal to what, v square by gy. So fr is equal to what, v by root gy. So this is the, always try to remember your Froude number is square root of what, inertia force divided by gravity force. Sometimes people what say the Fr is the ratio of inertia force by gravity force, but this is not the case, but it is the square root of the inertia force and the gravity force. So this is that. So Fr is equal to 1, then critical flow. In critical there are several features about the critical flow, we'll discuss in the later because let we discuss in the next class also if possible. And now if fr is less than 1, here I want to put it the less than 1, here subcritical flow, and if fr is greater than 1, it is supercritical flow. So that's it. Okay, and Reynolds, let me discuss the Reynolds number. We have also discussed, but rho v, here we will use the dh. dh, in case of pipe flow we have used these things. But in case of the open channel flow, what we will do, your Re is equal to rho v hydraulic mean radius by tube. For laminar case, for laminar, in case of the pipe flow, your value is should be less than or equal to 2000. Somewhere it is written the 2100 or somewhere 2300, but let us consider 2000 for laminar in pipe flow. So that is the value of, so this value is what for rho v dh by mu for this. But if we calculate in case of open channel, what will be happen? So rho v, at the place of RH we can put what? Your hydraulic mean diameter was 4 times of the RH. So at the place of RH, hydraulic radius dh by 4. So if we put here dh by 4 mu. So this value is how much in case of laminar? 2000. So here 2000 divided by 4. It will come out the 500. So in case of open channel flow, your Reynolds number is 500 for laminar. Similarly, for turbulent, it is, if it is 4000, in case of the, it should be the greater than or equal to 4000 in case of pipe flow, but in the open channel flow divided by 4. If you will divide by 4, it will come around the 1000 in case of open channel flow, your Reynolds number. So let me briefly written on the next slide. So your Reynolds number, let me put it in full view and fine. So your RH is, in case of pipe, what was rho v th divided by mu. In open channel flow, here Reynolds number, not RH. Rho v RH by mu, or we can also write rho v
Sir,
d.
screen is not visible, sir, your writing.
Oh, not visible.
Yes, sir. Empty space is there.
Okay, now I think it is visible. Now visible.
Ah, yes, sir, visible, sir.
Okay, RE is equal to, in case of pipe flow, rho v dh by mu in case of pipe, and RE in case of open channel flow, RH by mu. We can also write velocity into dh, this is the dh by mu into 4, because this, therefore, so your RH is equal to dh by 4 in case of open channel flow, in case of open channel. So your Reynolds number here for laminar, RE for laminar, it should be less than or equal to 2000. Laminar, RE greater than equal to 4000. Turbulent, but in case of your open channel, your RE less than equal to 500. Laminar, RE greater than equal to 500, 1000 for turbulent. In between transit flow. Here similar the case transit flow. So this is the about the Reynolds number in case of, so in case of Reynolds number, in pipe flow generally we consider the DH, that is hydraulic diameter. In case of open channel flow we consider the hydraulic mean radius. So now moving ahead, another thing, this is very important. One figure is visible, 13.2 figure.
Yes, sir, visible, sir.
This is the velocity contour actually, and here what actually this velocity contour means what? Nothing but Here and here and here, everywhere velocity is how much? 0.5. So contour is nothing but all, it is joining a line which join the all similar velocity point. So this is the contour, velocity contour. Similarly, these line having the everywhere 1.0 meter per second velocity, 1.5 and 2.0 meter per second velocity. Here one thing you can observe, as you and here we discuss about only one dimensional, that is the, if your channel is like that, we have considered only water is flowing in one direction, that is your velocity. If it is x direction, this is y direction, so your velocity, here we are discussing about the x velocity. Okay, so just observe here, this is the your wall, these all these things wall. So due to wall, no slip condition will be, you know already, no slip condition here will be 1. So due to the wall, your velocity at the wall will be 0 everywhere, your velocity, and the wall effect propagated towards the main channel, towards the main stream channel, towards the main stream. So here your velocity is 0.5, here 0.1, here 0.1.5, not 0.1, 1.0, here 1.5, here 2, here 2, here decreases, that is 1.5, then 1, then 0.5. So, and if you check from the bottom, you can also see at the bottom your velocity is less, at the top your velocity is more comparatively. So due to the wall effect, this velocity reduces, and in the main, that is the in the mid of the channel, your velocity is very high comparatively to the side, bank side of the velocity. Okay, so if you will now, let me draw some velocity like that. If you will draw at this point, I want to draw the velocity, what will be happen? At the bottom your velocity will be 0, but little bit up your velocity is how much? 0.5. if this is your velocity, so here the vector length represent the magnitude. So little bit above 0.5, little bit above 0.1, little bit above 1.5, little bit above 2.2. So your velocity is varying like that, and after that it might be your wall effect may be negligible, so your maybe velocity will be similar everywhere. So that is the, it reaches the u infinity. We will discuss, I think we have already discussed about the boundary layer concept, so like that. So hope, I think you got this concept what I was telling. Yes, okay. So this is a very fundamental concept regarding the velocity contour and all. Okay, now moving on the next slide. So actually uniform and varied flow. Today was topic also, the open channel flow and uniform flow. So here the uniform flow and varied flow. So in the below figure you can see this is the uniform flow, gradually varied flow, rapid varied flow, then gradually varied flow and uniform flow. If somewhere this type of stepping is there in the channel, what will happen? Previously and the upstream your uniform velocity will be, your uniform flow will be there, but after just just upstream of the your step, your gradually varied flow, if you will see here clearly, your depth of the flow is little bit lower, very slowly, but after that if you will see your depth is very fast, and in the short length, very fast and in the short length is reduces. Yes, is a very low and after is very, and after that here your velocity is little bit down down down, and after that it will gain the uniform things. So rapid varied flow, it is a short phenomena, not for a long reach. It is a short phenomena. After that, what and the water flow will try to gain the uniform flow. Always try to gain the uniform flow. So rapid varied flow is nothing but in a very small reach, in a very small length, your depth is varying rapidly. So this is that. So you can also read the, I have put it all the things here. Non-uniform, it come under the non-uniform. So this is that. Okay, let me read the basic things here. The flow in open channel is also classified as being the uniform and non-uniform, also called varied. So non-uniform comes, actually varied flow is comes also known as the non-uniform flow. Depending on how the flow depth, we are talking about here depth, flow depth, the distance of the free surface from the bottom of the channel in the vertical direction. So depth means here is nothing but, depth means is that if your channel is like that, your depth is this. But if channel is like that, in vertical direction means your depth is this, not this one, normal to the your depth. So this is depth. So we are talking about this. If this is the bottom, so this is the rated. That what is the depth? Flow depth, the distance of the free surface from the bottom. Distance of the free surface from the bottom. That is, this is the from the bottom. The channel measured, bottom of the channel measured in vertical direction, okay, varies along the channel. The flow in channel is said to be uniform if the flow depth remain constant. If the flow depth remain constant, then it will be the uniform flow. Otherwise the flow is said to be non-uniform, that is a varied flow. It may be gradually varied flow and it may be the rapid varied flow. Both comes under the non-uniform flow. Okay, so I think hope you got the point, and here the Reynolds number is defined like that for laminar and turbulent, that is a rho u r h by your dynamic viscosity, and the kinematic viscosity is nothing but your dynamic viscosity divided by rho. So if you will replace this, you will find. Now moving ahead, what I was discussed previously, this is given here, hydraulic radius and hydraulic diameter. You can go through the this slide, you will be easily find out, you will be easily able to understand what I was telling. But somewhere your Reynolds number, like in this book I think considered not 4000 for turbulent, but standard, if you're like the in case of pipe flow, if the Reynolds number in case of turbulent flow is 4000 or greater than 4000, just divide the 4, that value will convert in the for open channel. So here one line is very very important. The Reynolds number, the Reynolds number associated with water flow in open channel is typically above 50,000, and thus flow almost always travel or turbulent. Remember, in open channel flow, your Reynolds number typically, not always, your Reynolds number typically 50,000. So always in case of open channel flow, your flow is turbulent. Let me check your connection and all. Okay, slide is visible and whatever I am writing, it is visible to all.
Sir, visible, sir.
Only you are joined. Okay, no problem. After 5 minutes, we'll take some 5 minute break. Then we'll move ahead. Okay. So now moving on the next. So what I was discuss about the fruit, this is only. Okay. A specific energy, very important thing. So I will discuss after 5 minutes. Let me. So this is a very
Okay, sir.
important thing. Let me go for some water. Okay. After 5 minutes, I will discuss.
Okay, sir.
Okay. You just wait here. Okay, now I am audible.
Yes, sir. Audible, sir.
Okay, okay. So let us discuss about the specific energy. Before discuss about the specific energy, let us try to understand the Bernoulli's equation, because we using the Bernoulli equation we only discuss about specific energy. So let me go on the blank slide and let me write something. Okay, so Bernoulli's equation is nothing but, if you will consider, let me consider the first coordinate system. This is x. One fluid particle, let us consider one fluid particle is moving in the direction in the flow field along a streamline. Let us consider a streamline, and fluid particle is like that. So here what, the pressure force is acting from both sides, and one weight component is there, W cos theta, and this is W sin theta, and this is your weight of the fluid particle. Here is what actually your pressure is P, and a small area dA. Here is pressure little bit higher, P plus delta P, and a small area dA. So this force is acting on that. So what we consider, basically we derive the Bernoulli's equation. First we assume no viscosity or non-viscous fluid. So viscous force, due to the viscosity we will not consider the here force. So only two things. This is the first assumption, not viscous. Flow, your fluid is not viscous. Okay, this is the first assumption. Let me write here. So if you will apply here the your fundamental equation, that is a Newton's second law, summation of force is equal to mass into acceleration. Acceleration, you know already what acceleration is, du by dt, plus if we consider about the velocity not in the x direction, whole velocity, so dv by dx, and here into v multiplied by these things. Okay, if we, this direction is fs, so this replace we can by s. Okay, like that. So now if you will put here, what will your PdA plus, that is the your force is in this direction only, so minus P plus del P into dA minus W sin theta equal to what? Your mass into acceleration means dV by dt plus V dV by ds. Not here is a complete thing, dV by ds. So, and mass, what is the mass of your, you know already, density is equal to mass by volume. So here rho into area into length. Okay, or length is nothing but ds, because this is s direction, so if we consider here ds. Okay, so mass is this much. So here dA PdA minus PdA minus dPdA minus W sin theta equal to, m is equal to rho dA ds and these things dV by dt plus V dV by ds. So PdA and PdA is cancelled out. Here remaining dPdA minus W sin theta is equal to these things rho dA ds dV by dt plus V dV by ds. Here sin theta is what actually? If you will calculate the sin theta, what will be the sin theta? Sin theta is nothing but your ds by, if we go from the very basics, dz by ds, your sin theta. What is sin theta? Your perpendicular divided by hypotenuse. So your perpendicular is this and dh, and your hypotenuse is ds. So sin theta is equal to dz by ds. So this is that. So if you will put here dp by dA minus w sin theta is nothing but dz by ds equal to rho dA ds. These things only I am writing here. So not hard and fast. Dt plus V dB by ds. So this is that. Now here one thing we can also consider. The thing is your flow is steady. Here is the second assumption. Steady flow. If flow is steady, your dV by dt equal to 0. So now what is remaining? Remaining things only here. And what is your W here? W is what will be rho dA ds into m into g. So here g. So this is that. So put everything here. So dA, this is dP, whether I am online or not. Yes. So here dA and dP minus dP into W is what? Rho dA ds into g sine theta is dz by ds, and here is the same thing, that is your rho dA ds, and dv by dt is equal to 0, so only v dv by ds. So this is the equation. Now dA, here dA and here dA cancel out. ds and ds cancel out. Here ds and ds is cancel out. What is remaining here? Here remaining rho dv v. Here what is remaining? Rho g dz. Here what is remaining? Minus dp. So this is. Now coming on the next. And whatever here we have used the velocity, this is the average velocity, v average. I will come on the next on the average velocity. This is very important for understanding. Okay, so if we divide the rho, your minus dp by rho minus gz dz equal to dvv. So if you will integrate these things, what will happen? Let me put all the, okay, so here your integration minus your dp by rho minus here the g into z, or you can say the depth. Let me put it here the z, no problem, and equal to v square by 2g, v square by 2, and some constant is there. Some constant you can put this side also, no problem. Some constant is there. So because this term will give the another constant, this term will give the another constant. If you will add one constant common, I would like to add this side. So what is v square by 2, and these things I am putting in this direction, plus dp by rho plus gz equal to your only constant is remaining this side. So this is that. Now moving on the next slide, we are close to. So what is final expression? dp by rho plus gz plus v square by 2 equal to constant. So this is a Bernoulli's equation for, we have assumed two things. What? Non-viscous and steady flow. And another thing, velocity is average. Average velocity distribution we are talking about here. Average velocity distribution means what? Your velocity in case of pipe, what is this type of your velocity? Parabolic. But here we are assuming what? Your velocity is like that, uniform velocity. This is not the actual case, but for mathematical simplicity we have assumed these things. And cover these things, these parabolic things, we have defined one thing, kinematic correction factor, that is alpha. If your flow is uniform flow, if your flow is uniform, then alpha is equal to 1. If we here let's suppose at that point your velocity is v, then at that point your velocity is v average. At that point v average is equal to what? V into alpha in this diagram. But flow is uniform, then alpha is equal to 1. So what will happen? Your v is equal to, if flow is uniform, then alpha is equal to 1. So here we have not used the alpha term, so another assumption is uniform flow. This is a three assumption. If flow is incompressible, your rho will be constant. So what will happen? If you will integrate, that is p by rho plus gz plus v square by 2. Again another constant, and constant, again constant. So if you will divide by g, so p by rho z plus v square by 2g plus g, that is your z, is equal to, again you will divide here g is always constant, 9.81 meter per second, a meter per second square, so again constant. So this is the Bernoulli's equation. For what? We have assumed four things: non-viscous, steady flow, uniform flow, and incompressible flow. So this is four assumptions. Always remember. And this constant, how you will calculate? Let us suppose you want to calculate the everything at this point. At the initial pressure, velocity, and your head, that is your datum head. If you will know, then you can calculate this constant and you apply at that point, then you will easily find out the unknown things. So this is that. Now coming on the specific energy, always remember here what we have considered: uniform flow, steady flow, non-viscous flow, and the incompressible flow. Now come on the expression. Here we have used the similar things. These things we have used. Your h is nothing but the total head, or constant you can say. So total head always will be constant. So your z, pressure head, and this expression with the lots of assumption. Assumption is non-viscous flow, steady flow, uniform flow, and incompressible flow. Now coming on the specific energy part. In the specific energy, basically we considered only specific energy actually defined as the if we consider the Bernoulli equation and datum as a bed of the channel. Let us suppose here the figure is there, but let me draw for your. And why energy? Because of the all term is represent the energy. This is the kinetic energy, pressure energy, and the datum energy. So this is the channel bed. Previously datum was, that is the reference datum was the distance between the datum and bottom. But if we consider the bottom as a datum, what will happen? Z will be 0. So your equation will remain only h is equal to what? P by rho z plus v square by 2g. Always remember the assumption will be there in the specific energy also. During the derivation we have not assumed any assumption, but assumption is there. Always remember, because this thing is come from the your Bernoulli's equation directly. So your pressure is, here pressure is rho gh. We have considered the uniform flow. In case of uniform flow, your pressure variation like that, and you can also write the rho z y. So that is the hydrostatic pressure condition. Here hydrostatic pressure distribution. Here one thing was always remember, here we have used the hydrostatic term, but in case water is moving in, water is flowing, so you not confuse. Here we have used the hydrostatic, because if your water is static condition, then your pressure distribution is similarly like rho gh. In case of uniform flow, steady flow, your pressure distribution similar like the static. So that's why we are, for flowing water with uniform and steady flow, we assume the head pressure distribute the hydrostatic, follow the hydrostatic distribution. So that's why. So if we put here the pressure is equal to rho g y, then what will happen? Your rho g will be cancelled, only remaining the y plus v square by 2g. So this is that. This is your hydro. This is your specific energy term. So with this specific energy, we have the this graph itself a big deal. Let me discuss because it is very important for a hydraulic engineer. Okay, now I want to take new slide. Okay, so a specific energy now we have defined, E is equal to y plus v square by 2z. So here the for making the graph it is very difficult because it's having these two term, one the parabolic term and one is the without square term. So what actually we do, first we try to find out the asymptote. Asymptote is nothing but it is a straight line which asymptote, first we try to find out the asymptote of this equation. Asymptote is nothing but asymptote is nothing but is the it is a straight line which at infinity your graph of this equation may be the very closer to this line but not touch. So this is the asymptote. For this equation we have two asymptote. What? One is E is equal to y, another is y is equal to 0. So y is equal to 0 line is this, if you will consider this E and this is y. So at this line your y is equal to 0, this is asymptote, and at this point your E is equal to y, that is your, no, E is equal to y means what? Y is equal to mx plus c. So how you will draw this line? If c is there, so from here you will draw the one line. So y is equal to E is equal to y means is nothing but this is the, your line will start from this, from origin, 40-degree line, and your graph, your the graph of this equation will come between, will draw between these two line only, not beyond these two line. So what will it will become like that? At the infinity it may be the very closer to the your y is equal to asymptote, any asymptote, and then it is here not, it will be touch. Okay, so let me smoothing. So this is like that. Okay, so at that point your specific energy is minimum, and at this point we know the this point as a critical depth. Above this subcritical, y sub, and below this y super. Okay, so this curve itself having the lots of characteristics. So, and how you will find the asymptote, this is a very important because in many books not very clearly defined, but in some lots of book is there which is very clearly defined how we will calculate the asymptote. So this figure is given, so this figure we'll discuss later. Let us discuss about the how we will calculate the asymptote. If you will put your equation is like that, E is equal to y plus v square by 2z. If let me first convert in the your unit weight, so your discharge is equal to what? Area into velocity. Area is equal to your b into y into velocity. If q by v, y into velocity, so this is represented by small q, and this is known as, generally we know about the unit discharge. So unit discharge is equal to y into v. So v is equal to unit discharge by y. Let me put it here, y plus q square divided by 2z y square. So this is E. Now in this equation, if your channel width is constant, if your channel width is constant, this is constant. So in this equation, only this y is variable in this direction. That is the right hand side. Only y is variable. Now we can compare. Here the velocity was variable, but if we your width is constant, that's why we convert in the single variable in the right hand side for comparing, for calculating the asymptote. So basically if you will put y is equal to, let us, infinity. Infinity means very, not infinity, tends to infinity. If you put about, that is a very big number. If you will put here very big number, then what will E is equal to your very big number here. Let us suppose very big number represented, I am representing with the that is capital X. If I represent very big number, if you will capital X here at that place of y, and plus v square by 2g and y square, very big number. If you will, this is a very big number, if you will square it, then what will happen? Again it will be the very big. And when you will divide with this number, your this term almost negligible or very close to the zero, very negligible. So E is equal to y. E is equal to what? Your very big number. And at that place, very big number, what? Your y, we have put the very big number. So one asymptote is y is equal to, E is equal to y. So this is that. This is the first asymptote we calculate. We put the extreme. We put the extreme value for calculate the, in any equation. In any equation, if you want to calculate the asymptote, you can put the very extreme point value. Then you can easily find out the asymptote of the given equation. Now coming on the second asymptote. If you will calculate the second asymptote, what will, now put the value of y as a 0. Very, not 0 but tends to 0. If you will put, what will happen? E is equal to, this will be very less number, let us represent with the m, very small m. So very less number plus q square divided by your 2g and y. Y is very small number, that is a small number. If it will be square, then what will happen? This small number will convert in the another small number. So your E, this is a very small. This is a very small. So your E is what at that, at 0. At 0, your E will be very maximum. What? Q square. If you will divide anything with a very small number, then the whole term will be the very bigger. That is the very bigger term. So if E is equal to x, E is equal to x. So second asymptote is what? at the extreme point of the E, your y will be 0. So this is the second asymptote. So at that process, with that process, we calculate the asymptote of a given equation with this process. So now hope you will. Okay, I have lost the connection. Why? I don't know. It is working, but why I lost the connection? Is there any difficulty? So almost fine everything. We have already in connection, then why it is not? Okay, not connection, but connection is there. Okay, so some network problem. Okay, sorry for interruption. Okay, anyway, video is recorded, so let me moving ahead. I think no one joined, so sorry for that. Okay, okay, let me finish my point. What I was telling. Okay, with that we calculate the asymptote like that. We put the extreme value always. Let me share the screen. If somebody join, then he can see the my screen. He or she. Okay. Okay. So with that we try to calculate the asymptote things always. So this is that. So with that we derive this equation, and if we will solve the this equation for a particular constant E, you will get the three y value, y1 comma y2 and y3. One is 2 is positive and another is negative. For a particular E, for a particular E you will get the 3. This is the negative line, but negative depth is not possible, so we not consider these things. Always two depth. What was one is the subcritical and another is the supercritical at a particular E. These two depth is possible. So in this figure only these things is represented. At that point your YC, that is your critical, at that this is the minimum specific energy, and this is the specific energy line, and this is the depth line, and your this first asymptote, and this is your second asymptote, y is equal to 0, and in this above the your subcritical, that is fr is less than 1, below the f supercritical, fr is greater than 1. Up to this line, up to this line your represent y, because this is a 45 degree line. If 45 degree line, this depth and this and this will be equal. So if it is y, then it will be also y. So this is represent the y, and the remaining term is represent the your v square by 2z, because this line is represent what? This line is represent your E. How much E? How much E? E is having the two term y plus v square by 2z. If up to this line your y represented, the remaining thing is represent the your velocity. Now if here, if you will check here, your depth is very high. Your depth is very high, but your velocity term is very less. So in generally in case of the subcritical flow, your depth is much, but your velocity is less. But in case of the supercritical flow, what will happen? Your depth is very less, that is your y, and the velocity magnitude, that is your v square by 2z, is very high. In supercritical flow, your velocity is very high, and depth is very less comparatively the these things. Then if, for example, if you want to know whether your flow is supercritical or subcritical, what you will do, if your velocity is very high, if your velocity is very high, if you drop one stone in the flowing river, what will happen? If you will drop a stone in still water, what will happen? Your wave is traveling in both direction. Your wave will travel in the both direction, but here not the still water. Water is moving. If water is moving is very fast, that is in the supercritical flow, what will happen? Your wave is moving in this direction only, because due to the velocity is very high, so your wave velocity is not much. Your wave velocity is not much, so at that point your wave will not move in the upward direction. So in case of supercritical flow, if you will throw a stone in the river, if your wave is not moving in the upstream, then you will identify this flow is the supercritical flow. But how much value, how much the value of the float number, this is you cannot calculate, but qualitatively you can tell the water is flowing in the under the supercritical flow. Then how you will calculate the subcritical flow? In subcritical flow, your wave is moved in this direction, downward direction it will be moved, but in the upward direction it will also move. In case of the subcritical, if your wave is moving in the both direction, then you can easily tell qualitatively your water is flowing under subcritical condition. So this is the basic, not the overall of the open channel flow, but this is the basic behind it. There are lots of characteristics in the open channel flow itself, a big research. Now moving ahead, we have discussed lots of things. Now whether anyone join or okay, that was my mistake. Okay, no problem. Sometimes we have the network issue in IT Guwahati, but not every time. Now network is fine. Okay. Now here is nothing but what I was discussed. This is only that thing. Okay. So E minimum, if you want to calculate this, it is written here. If you want to E minimum is what? At the your critical velocity, v square by 2g. So this is that. And E minimum means your fluid number is how much? Your Fr is equal to V by root G. Why? At the critical condition, it will be equal to 1. Your velocity is equal to what? Gy. That is Yc at critical. Fr critical if we talk about. So your V is equal to this. If you will put here your critical velocity, so E minimum is Yc plus V square. If you put here Gyc divided by 2g. So G cancel. So here Yc plus Yc by 2. So here how much you will get? 3 by 2 Yc E minimum. So this is that. Okay. Your fluid number is this is only valid for the rectangular channel. Why? Because your fluid number is, if we go above, I think from where, here is a LC. Your fluid number is, length parameter is V by GLC. LC is nothing but it is the characteristics length. LC is the characteristics length. It is taken to be flow depth Y in the wide rectangular channel. Is wide rectangular channel, LC is equal to Y for wide. So whatever we have discussed up to that, it is valid for rectangular channel, because we have considered Fr is equal to what? For all calculation, V by Gy. And what is LC? LC is area by top width. For rectangular channel, if you will calculate LC, your area is B into Y and top width is B. So it is only Y. So with that you can also calculate, no issue. Now moving ahead. Okay, so the question is, the question 3, the flow characteristics of a channel do not change with time at a point. What type of flow is it? Whether uniform flow, non-uniform flow, steady flow and unsteady flow. Have 1 minute time. Anybody joined or not? Only one join. Okay. So the question 3 is flow characteristics of a channel do not change with time at any point. What type of flow is it? Let me go back on PPT. So basically what is telling, if it is a channel like that, someone joined or not? Okay. If it is channel like that and water is flowing in this direction, So do not change with time at any point. At any point means what? At this point, 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 at this point. If velocity is 5 meter per second at t is equal to 8 pm or am, whatever I am taking the 8 pm. So what will here also velocity is 5 meter per second, 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 5 meter per second. This type of flow we know generally about the uniform flow. If and if t is equal to 10 pm, then maybe velocity will be changed around 6 meter per second, but every point 6 meter per second, 6 6 6, everywhere 6. What is a steady flow? Steady flow is at a every time, at a not particular time, that is every time your velocity will be constant. At 8 pm your velocity will be suppose 3 meter per second. At 10 pm also 3 meter per second. Here may be the 5 meter per second at 8 pm or 10 pm. Here may be 10, here may be 10 meter per second, here may be 11 meter per second, but with time at a particular point your velocity will be constant. So this is the steady flow. Now the question 4 is the specific energy of a flowing water in rectangular channel of 5 meter width, 5 meter width, 2 meter depth, and discharge is given q is equal to 10 meter cube per second. What is the specific energy basically is talking about? So please within 2 minutes, then I will start. Let me calculate. So specific energy is nothing but we have discussed lot. Here the all assumption is there. What assumption? Your uniform flow, then steady flow, then your hydrostatic pressure distribution, hydrostatic pressure distribution. Previously I have discussed. Please go through the just couple of back, couple of back, couple of minute back. So pressure distribution is hydrostatic pressure distribution. During the derivation of hydrostatic pressure distribution, we have assumed your channel slope is very negligible. I have not discussed the derivation of the hydrostatic pressure distribution, but some later I will discuss. Negligible. So here the slope is very less. That is almost equal to 0. So this is also assumption. Now what another assumption? Your flow is incompressible. Another is whether I am non-viscous. Non-viscous. So with this assumption, your study, that is your specific energy formula, is V square by 2c. Here alpha is 1 because of the uniform velocity distribution and uniform flow. Uniform flow, and we are using the average velocity here. So now your y is equal to 2 meter plus your discharge is equal to 10 meter cube per second. Discharge is equal to, you know already, area into velocity. So discharge by area. Discharge is 10 and area is 2 into 5, that is 1 meter per second. So 1 meter per second, if you will put here, that is 1 square divided by 2 into 9.81. If you will calculate these things, it will become around 2.05 meter. So this is the first option is correct for this. So always remember, before applying the any equation, that is the engineering equation or any equation, you just recall the assumption behind the equation. Then you will easily understand and enjoy the solving the problem. Now moving ahead on another things, that is the if the depth of water in open channel is less than the critical depth, that is the your depth of water, that is the normal depth of water, is less than critical depth, the flow is known as what? It is the torrential flow, tranquil flow, critical flow, and the turbulent flow. Is within 1 minute try to. Okay, so the supercritical flow is also known as the torrential flow or the shooting flow. Torrential flow or the shooting flow. So here is the your, that is the your depth is below, so it is the supercritical flow, but it is also known as the torrential flow. Always, because its name suggesting the torrential means very high velocity. Torrential flow and shooting flow also. So always remember, here some table is given. If the float number between 1 to 1.7, jump type undular, and your type of water surface is undulating. If in between 1.7 to 2.5, weak jump, a small rollers formation. If 2.5 to 4.5, oscillating, water oscillate in random manner. 4.5 to 9, steady. Your, we know the jump type is steady, roll, and the type of water surface, roll and jump action will be there. Greater than, it is a strong jump, very rough and choppy, your water surface. So now coming on the question number 7, the depth of water below the spillway after hydraulic jump are 1 meter, and 6 meter respectively. The head loss will be, what will be the head loss? This is the formula. You can calculate. EL is equal to Y2 minus Y1 cube 4 Y1 Y2. So you just put here your depth is how much? 2.7 minus 1.6 cube divided by 4, 2.7 into 1.6. It will come around, let me calculate, 2.7 in minus 1.6 power cube divided by 4 into 2.7 into 1.6. It will come around 0.077. Okay. Okay, this is the value 0.077. This is a your in a rectangle. The depth of flow is 1.6. A specific energy at that section. Okay, okay, okay. Okay. No, what was the formula actually? Okay, here is the this thing is given. Okay, I have used another term. So EL is equal to your Y2 minus Y1 cube divided by 4 Y1 into Y2. Okay, I was jumped directly on another question. So here the numerical value is 6 minus 1 cube divided by 4 into 6 into 1. So 5 cube 4 into 6. So 125, then and it will come around 5 point something 2. So A option will be correct for this. Question 8. In open channel flow, for best efficiency of rectangular section, the ratio of bottom width to depth width is equal to what? Best efficiency channel of the rectangular section. So bottom width and depth y, what will be the? Just please try to solve this. The ratio of bottom width to depth. So after calculating these things, your width should be equal to 2 times of your y. Now this is wrong. This is not correct. For this question, not correct. Okay, so in rectangular channel, I think time is over. For in rectangular channel, the depth of flow is 1.6 meter and the specific energy, that is your E, is given 2.7 and the depth is given, Y is given 1.6. The flow condition is what? Whether it is subcritical, supercritical and the critical flow. So just try to calculate. How you will approach this problem. Depth is given, specific energy is given. So a specific energy is nothing but E is equal to Y plus V square by 2Z, and put the value of Y and get the value of E V from here and calculate the FR is equal to V by 2Z, and using the FR value you can calculate these things. Now question 10. A 1.2 meter wide rectangular channel bed slope is this. The Manning's coefficient 0.01 and carrying the discharge is 0.5 meter cube per second. The normal depth of the channel is what? So you know already the Manning's coefficient is V is equal to Manning's formula of velocity V is equal to N 2 by 3 h to the power 1 by 2, and discharge is equal to area into V. So with this you can calculate your R is equal to, you know already, area by perimeter. So in area by perimeter, this is a wide rectangular channel, so R is equal to Y. So you will put at the place of R, you will put the area. Area means your B into Y into R is Y by 2 h to the power. Put the all value here, only the 1 by n is there. Here only your y is unknown, so you can calculate y from here also. So that's all from my side for today. We'll meet again on the next class. Okay, thank you all.